Welcome back. So you'll recall from the whiteboard lecture that the equations we want to solve are the linearized shallow water wave equations in one-dimensional, and those are given by first the momentum equation du dt is equal to minus g dh dx. So g dh dx is the pressure gradient force, and it's down gradient, so it's in the minus from high sea level to lower sea level, and du dt is the acceleration. So this is the pressure force per unit mass. And then we also have the continuity equation, which is dh dt is equal to minus h du dx. So here on the right hand side we have the convergence of mass due to the convergent currents, and because u doesn't depend on depth, we get the convergent multiplied by the depth of fluid h. And we showed that these two equations can be combined by taking a t derivative of the second equation and substituting in the first one. We get the wave equation, which is d2 h dt squared minus c squared d2h dx squared is equal to 0. This is the wave equation, where the wave speed c is equal to the square root of gh, which is the speed of the very long waves, or the shallow water waves, where the wavelength is long compared to the depth of the ocean. And we showed that the solution to the wave equation, the general solution, is this one: h of x and t is equal to some arbitrary function f of x plus ct plus some other arbitrary function g of x minus ct. So this gives us the sea surface height. If we want to recover this here gives us the sea surface height. If we also want to get the velocity u, how do we get it? Let's label our equation. This here is equation 1. This is equation 2. If I take the solution and I differentiate with respect to t, so d by dt of h of x and t, that's equal to derivative of this with respect to t, which is going to be f primed, derivative of f primed times x plus ct, times the derivative of the inside. We have to use the chain rule, and that gives us c, plus, and then the derivative of this term with respect to t, and that will give us a g primed of x minus ct, and then by the chain rule we differentiate the inside, we get a minus c. So this means that du dx, which is equal to dh dt divided by minus h, is equal to minus 1 over h times c f primed x plus ct minus c g primed x minus ct. And we can integrate with respect to x and to get u. So u of x and t is equal to minus c over h f of x plus ct minus g of x minus ct. And so now we have both the solution of h and u in terms of two arbitrary functions, f and g. So how does one determine these arbitrary functions? Well, we need to go back to the initial conditions. So you'll notice that from the wave equation, it's a second order differential equation in time, so we should have two initial conditions. Or if we go back to the original equation, we have two equations, both are first order in time, and that also will give us two conditions. So let's pick a problem. Suppose that we have the following situation. So at t equals 0, so we have initial condition, at t equals 0, h is of the following form. This is x, and this is h of x at t equals 0. This is A, this is B. And the solution looks like this. It's 0 out here, then it shoots up to a value of 1, and then it's a constant, and then it shoots back down. So this function here will give this a name. This will be m of x, which is equal to 1 if a is less than x is less than b, and 0 otherwise. So the initial condition is h of x and 0 is equal to m of x. And we also need an initial condition for the velocity, and for that we're just going to assume that the fluid is at rest. So u of x and 0 is equal to 0. So it's as if we have a dam, two walls here holding the water in place, and then at t0 we remove the dam, and then the water is allowed to flow out. Alright, so if we use those conditions, then we know from the definition of h that we know that h of x0 equals to f of x plus g of x, that is equal to m of x. And for u, we have u of x and 0 is equal to minus c over h f of x minus g of x is equal to 0. So from the second of these equations, we know that f of x must be equal to g of x. And then if we use the first equation, if f and g are equal to each other, then they must both be equal to a half of mx. So therefore the solution is h of x and t is equal to m of x plus ct divided by 2 plus a half m of x minus ct. And u of x and t is equal to minus c over h 1/2 m of x plus ct minus 1/2 m x minus ct. And so what happens is that the solution, which breaks up into two waves, one traveling to the left and another one traveling to the right, they have the same shape as the original box, so they'll create a box, but they're each half as high. So this initial box will break up into two boxes of half the height. When they're at t0, they're superposed constructively and give us the full height, but then they separate, one going to the right, one going to the left, and one going to the right at the same speed, c equal to gh. And the velocity will be given by this one. So there'll be a wave train moving to the right over here and one moving to the left, and they will be, the velocity will have a boxcar shape, except it will be multiplied by minus c over h. Alright, so that's the solution. Now that's the case where there is no rotation. Remember here, we're ignoring, well, let's remind ourselves of the assumption. So we ignore rotation, we ignore friction, and we also ignore all the nonlinearity. The momentum and vection terms like u, du, dx, and so on, those are ignored. And also it's symmetric. There's no variation in the y direction. Okay, so that's the setup. Now we're going to go to the code. So I have my MATLAB, here I have my text editor, on the left, and on the right I have my MATLAB window. I've already written the code, so let's go through it and then we'll run it. So it's going to solve the 1D shallow water wave model with no y variation. I've written it in such a way that we could include rotation and friction if we want to, and we will do that in just a little bit, since our goal ultimately is to study the geostrophic adjustment problem, where rotation becomes important, the Coriolis force. But at first we will set it to 0. Alright, so du dt, that's minus fv, is equal to minus g dh dx minus ru, where r is the friction coefficient and f is the Coriolis parameter. and then dv dt plus fu is equal to minus g dh dy minus rv, and dh dt, which the continuity is h times du dx plus dv dy. Now, since we're assuming there's no y variation, dv dy will be 0 and dh dy will be 0. So these equations can be written in vector form, where the state S of the model of the ocean is set up as a 3-variable system, u, v, and h. So the time rate of change of the state is equal to, and then since the equations are linear, they can be separated out in more matrix form. So we have the state S, u, v, and h, and this matrix operator, differential operator. Right, the 0 multiplies u because there is no u over here in the wave part. There's a frictional r times u over here. Minus f multiplies v, and g dx applies on u. The reason there's no minus here is because we're on the left-hand side of the equal side, so I moved this term over to the left-hand side. Then the second row is for dv dt, so we have f times u, and then 0 for everything else, and then minus r times v from the friction term. And then finally the continuity equation, since there's no y variation, it's just h d by dx of u. And there's no friction in the continuity equation. So the reason we separate it out into 2 blocks, one involving the wave part and one involving the friction, is that we're going to use a different time stepping scheme to integrate the wave and the friction. And the reason we do that is because the leapfrog scheme is a good scheme when there's no friction, because it conserves the energy. So we'll use the leapfrog scheme for this part of the equation, and just a standard Euler forward for the friction part of the wave model. And so the leapfrog scheme, we go from time t minus delta t and we go to t plus delta t. So that's a separation of 2 delta t. So we divide by 2 dt, and on the right hand side we have m times the state minus r times the state. For the leapfrog scheme, we evaluate at the midpoint for the wave part, for the dynamics. So that's at time t, right, in between t minus delta t and t plus delta t. And for the friction, since we're using Euler forward, we're going to use it at t minus delta t, the same one as where we're starting this interval. And if we solve for s at t plus delta t, it's equal to s at t minus delta t plus 2 dt times m times s plus r times s. And again, this one's at time t, and this s is evaluated at t minus delta t. So that's what we're going to code below. All right, so then let's go down the code. G is the force of gravity, 9.81. H is the depth of the ocean, 4,000 meter. C is going to be the speed of the waves, root gh. Omega is the rotation frequency of the Earth, 2 pi divided by 1 day, 24 hours, 60 minutes, 60 seconds. Phi 0 is the latitude at which we're going to evaluate the Coriolis parameter. So we're going to pick it at pi by 4, which is at 45 degrees north. And then F is 2 omega sine phi 0. RD is a quantity called the deformation radius, the Rossby deformation radius. And you can think of it heuristically as the distance a gravity wave will propagate in 1 day, or more precisely in one period for F, 1 over F, which has units of time. Remember, F is a frequency as units of inverse time. And so this is basically, RD is scales like the distance a wave will travel before it starts feeling the effects of the Earth's rotation. R is a friction parameter, and we're going to set it to 0 in our first demonstration. And we're also going to ignore the rotation of the Earth, so we're going to set this to 0. So the first time through, we'll have no rotation and no friction. N is the number of mesh points, so we have 10,000 mesh points. Since we have only a 1D problem, we can afford to put a very high resolution. So we use 10,000 mesh points. Our domain size L is 10,000 kilometers, so we have 1 kilometer resolution. And A is going to be the amplitude of the initial disturbance. So the first one we're going to do, we're going to try an initial condition, which is down here, which is just going to be a Gaussian hump of water, like a bell-shaped distribution. Okay, so A is going to be the height of that, and sigma will be sort of the half width of that bell-shaped distribution. So we pick that to be L divided by 100. So that's about 100 kilometers. And so this is for the parameters. Then since we're doing a finite difference solution, we're going to discretize the domain from 0 to L with n plus 1 points. It's going to be periodic in the x direction, so the point at L and the point at 0 are really the same point. That's why I put n plus 1, and then later on I'll throw it out. So the next line, I get rid of the last point, because it's really the same thing as x equals 0. And then the mesh spacing dx is x2 minus x1. And then we do the differential operators using the permutation using I and permuting its rows to get a permutation matrix. And we do that to get the point to the right minus the point to the left divided by delta x. Or I should say the point to the right minus the current point divided by delta x. That's the gradient, and then minus the transpose of the gradient is the divergence. So it's a little bit silly in one dimension, but this method of doing the differential operator generalizes to higher dimensions. And then we create this M operator over here, the same one that we have over here. So the first block is 0, the second block is minus f times I. This will just be zeros again because we're ignoring rotation the first time through. Then the pressure gradient, G times grad, which will operate, since it's in a third block, will operate on the H term. The second row will not do anything because there'll be no velocity into and out of the domain. It'll be all in the along the x direction. And then finally the last row is for the divergence of in the continuity equation of u. Alright, and then I have a block here to make friction parameter. We're going to ignore that because we're not going to have friction the first time. I'll come back to it later. Alright, down here we have the time step size delta t. And this is something I haven't talked about yet, but for these problems where we have wave propagation in finite difference, the discretized numerical scheme is only going to be stable if we do not let the waves propagate across one full grid cell within 1 delta t. In other words, we have to pick delta t small enough so that a wave within one time step cannot travel right across one full cell. So since the grid cell is delta x, if we divide delta x by c, we'll get a time, and that's the time it would take for the wave to cross the grid cell. We have to pick delta t to be smaller than that for stability. So here I took it 20% of that, just to be on the safe side and for increased accuracy. All right, so that's delta t. And then the amount of time I'm going to integrate the model for, the simulation, is going to be 20,000 times delta t. So that's how long I'm going to run the model. All right, then we need to specify some initial conditions. And so for this, I set t0, u0, v0, and h. H is this Gaussian, this bell-shaped curve of width sigma, and it's going to be centered at L by 4. So that's a quarter of the way of the 10,000 kilometer domain. So at 2,500 kilometers, at 2,500 kilometers, we're going to have a bell-shaped curve for the sea surface height displacement but no current, and then we're going to let that go and it's going to start propagating. So what we should see, if our analytical solution is right, should separate out into two bell shapes, half the height of the original, one propagating to the left and one propagating to the right. Alright, so then since we're using the Liebfrost-T, we set up this 3-time level. P and P1 are the indices to them. We initialize S of P1, so the first slice of that 3-state matrix, 3-state array, and we put in U and V and H for the initial conditions. And then if we want to retrieve U, then we pick out the first n rows of the state matrix. If we want to get V, we pick out the next n rows, and if we want H, we get the next n rows. So that's what these are, the indices to get them out if we want to plot them, for example. All right, so then to get the next time step, so to start off this leapfrog scheme, we have to sort of prime the pump. The first time step, we just do an Euler forward for all the terms, for both the friction and the dynamics. Oh, I forgot to add the friction to this, but it's 0, so it doesn't really matter, but let me add it. Plus dt times r times s of P1. Maybe I could put it like this, get rid of the dt. Alright, so the first time step is just a regular Euler forward, and then the regular time stepping. So we take the state at time p1 and we do minus 2. I have another error here. There should be a minus for this one. Okay, so we go S, the state at times p1, minus 2 delta t times m times the state at the midpoint, which is p2, plus r times s at the p1 at the initial state. This is the friction term here. And then we just permute the order of p1, p2, p3, and we just iterate forward. And that's going to march the state forward in time. And then every 100 time steps, we're going to make some plots. And I'm not going to go through the plotting. You'll see the figures when we run the code, and I will upload the code to the course webpage, and you can try it out yourself. Alright, so let's try it out. Clear all. So it was the bell-shaped curve, and sure enough, it's split into two, one propagating to the right and one to the left. And you'll see here, it's a periodic domain, so they go across here, they'll interfere constructively, and we get back the wave height of 10 meters, your initial one, and they will interfere again at the starting position. And they interfere back constructively, and then they separate back into the right and left propagating waves. Alright, let's stop it. Control C. We can pick a different shape if we wanted, so let me pick a different initial shape. H is equal to, so let's comment out the bell-shaped one, and let's put the box one. So this one I picked a box. It's a little bit smoothed on each side, but it's roughly just a rectangular box. So let's run that one. CLF, shallow water wave. And it breaks up into two boxes, one propagating to the left and one to the right. And now they're going to interfere constructively. They go back to a height of 10 meters, and they pass through each other. And the two waves, you have one each of 5 meters height. And they will interfere again constructively, and they pass through each other, and they keep propagating around and around and around. Alright, so the first thing I'm going to do is I'm going to add friction back to the problem. So we're going to add friction, and somewhere in this range over here, there'll be a region with some friction. So out here, there'll be no friction, so the wave will propagate, and you'll see that the amplitude of the wave will start decreasing as it propagates through the region of friction. So let me show you how I did the friction. So I just made the friction to be a function of space. So I'll put a keyboard over here, keyboard, so we can plot the friction term. Clear all. Well, first I've got to make the friction not zero. CLF. Okay, let's plot. And I made this ramp function. It's just a function of x comma ramp. And I multiply that by r to get the friction term. So the friction is 0. Let me set the font size bigger. And then let me redo the plot in kilometers. Alright, so this is the x-axis in kilometers, up to 10,000 kilometers. The friction is 0 all along here, and then around 5,000 or so meters, it starts ramping up to a maximum by the time it reaches 7,000 kilometers, and then there's a strong friction in this region, and then it ramps slowly back down to 0, up to 10,000. And so when the waves, they start over here, when they propagate into this domain, they will be damped, and you'll see what happens over time. So wave. Alright, so there it goes. Around here, we'll start seeing some friction. Oop, I can't put my mouse on there. It stops the film. The code stops when I put. You can see here, it started damping, and then the other wave from the right is damping. They interfere constructively, but they're still being damped as they go through the friction region. And then once they leave the region of friction, they pretty much conserve their wave height. They interfere with each other and pass through each other. And then they will propagate back into the region of friction. and get damped out again. And eventually the wave will completely damp out, because every time it's propagating around the periodic domain, it keeps going to this region of high friction and it gets damped out until there will be nothing left. And all you have is a uniform sea surface height, pretty much uniform across the whole domain. Okay, let's stop it. Go back here, now let's add rotation. Alright, 2 omega, so now we do have rotation. Now the speed of these wave, which is root gh, so the square root of 9.81 times 4,000 is about 198 kilometers per second, so it's very fast. And so the wave will travel quite far in one day, and that means we'll have quite a big Rossby deformation radius. So to do this geostrophic adjustment problem, so we can see very clearly what's going on, we're going to change the parameters of the problem so the waves are slower. And one way to do this is to imagine that the interface we have at the surface between the water and the atmosphere is really the interface between two layers of water in the ocean. This would be the sea surface at z equal to 0. We have an interface here at c equals to h, and the mean thickness of this layer is h, and this will be equal to 400 meters. So this is air. This is the top layer of density rho naught, and then below there's another layer of water rho naught plus delta rho naught. And this one is a layer of infinite depth, goes up to minus infinity. So we're going to imagine that we have a layer of water up here above a deeper layer of more dense water, which is maybe 1% denser than the water above it. And the effect of this will be that the buoyancy effect, when there's a wave pushing up or pushing down on the bottom one, the effect of gravity will be greatly reduced because the density differences between two layers is very small. And so in this case, the effective gravity, g primed, the reduced gravity, is going to be equal to delta rho naught over rho naught times g. And we're going to pick this to be about 0.01 g. So about 1% of the original gravity. And so the speed of the wave c is going to be equal to the square root of g primed times h, which will be equal to 0.01 times 9.81 times 400 meters. And if we put this into the code, g is 0.01, h is 400. I have a keyboard here to stop the code so we can look at the value. Shallow water wave, c, and is about 6.2. Okay, so let's run it. Shallow water wave. Alright, so the box separates, but now in the bottom panel I've plotted the v velocity, that's the velocity, into and out of the page. Because there's a Coriolis force, the gravity will push, pressure gradient will push currents in that direction, but the u velocity will generate a Coriolis force in the v momentum, in the y momentum equation, and accelerate velocities into and out of the page. And now something very different happens. There's that initial box of water. After we broke the dam, it radiated some waves, but it's kind of staying in place, right? And what you see is you have a kind of a jet of the current at around 750 kilometers. There's a northward jet, and there's another one at around 3,250 kilometers, one going southward. And so on the left side, over here, there's a current going north, and that means that there should be, if it's in geostrophic balance, there should be a high pressure to the right. And sure enough, there's the elevated sea level on the right. My hands are going the wrong way, so the the display is not a mirror image. So let me see if I can. There's two currents, and they prevent the water from slumping downwards. So you have water ramped up on one side, and the rotation, the Coriolis force keeps it ramped up, and that just stays there. So there's no friction over here. So this just stays forever. And the waves that radiate away, eventually they go through the friction zone and they get damped out. Let me stop it and run it again. Alright, so it breaks up into two propagating waves, but those waves will feel the currents generate a Coriolis force, and the Coriolis force interacts with it. Eventually those waves will radiate out into the friction zone where they get damped out, and what we're left with is the initial boxcar of 10 meters high kind of stays there. It only slumps down a little bit on the edges, on the right and the left. And it doesn't keep slumping down because instead there's a current flowing along the edges, and that current is generating a Coriolis force which is pushing and allow the water to stay piled up. And so most of the water of the original box at 10 meters stays there. And then you have a little bit of slumping on the edges, and some energy is radiated away in the form of waves. Most of the potential energy that was stored up in the box, or I don't know if most, but quite a bit of it, was transformed into kinetic energy for the jets flowing along the edges, and some of the energy radiated away, and there was some power dissipated in the friction zone. So it's remarkably different than the case when we didn't have rotation. All right, let me stop it. So in this case, we had a Rossby deformation of around 60 kilometers. So let's say I decrease it, move back. So it's about half as much. The speed is about half as much with the faster waves. All right, so that's the geostrophic adjustment problem. So the original hump of water, initially the force of gravity generates currents in the U direction, and the minute there's a current in the U direction, that will generate a Coriolis force into or out of the page, depending on the direction of the U. That accelerates the V component of the velocity, and that V component of the velocity then has its own Coriolis force in the X direction, which can balance the force of gravity. And what you're left with is a hump of water that just sits in place in this zone here with no friction. And some energy is radiated away as waves, and some power gets dissipated in the friction zone. But most of the energy stays in the original region as potential energy because of this hump of water that's just staying there, and a little bit of kinetic energy on the fronts, on the left and on the right. And kinetic energy in the form of these currents, these geostrophic currents that balance the hump and prevent it from slumping down. All right, so I'll upload the code to the course website and you can play with it.